Alright, so we've got the impulse momentum theorem that tells us how to figure out perhaps what final speeds are, things like that, and the impulse is related to a force that acts over time on an object. So here's a couple more voting questions associated with this. I just couldn't put them so many in a row before, so let's do a couple more and then we'll get back to new concepts. Two equal mass balls, one made of clay and one made of rubber, are simultaneously dropped from rest from the same height above a table. So they both move right next to each other the whole time, except the rubber ball bounces really high upward afterwards while the clay ball sticks to the table. Which ball has the greatest magnitude change in momentum from just before they both contact the table until just after the rubber ball leaves contact with the table? The answers are either one of those two, or they're both equal, or there's not enough information given. The answer has to do with the voting question that we did just in the previous video right at the end. One of the balls has an initial velocity and it's brought to rest, whereas the other one has an initial velocity going down and ends up with an initial velocity, a final velocity going up. So it's changed direction and it has a bigger magnitude change in momentum. Okay, the rubber ball is the one that bounces, has a bigger magnitude change in momentum. Look at the voting question we ended the last video with for a more in-depth explanation of that. Therefore, the rubber ball has the larger magnitude net impulse delivered to it. In other words, in the time of contact with the table, the rubber ball has two forces acting on it. The weight force pulling down on it and the contact force from the table going up on it, and they give some net impulse combined together to it. The rubber ball is getting a bigger net impulse delivered to it because it has a bigger change in momentum magnitude. Second voting question. A super ball, that just means a really bouncy rubber ball. It's dropped onto a table. Just before contacting the table, it's moving down at 1 meter per second. And let's imagine it's a perfect super ball, so after it bounces, it's moving up at 1 meter per second, from just before to just after leaving contact with the table. During the time of contact with the, it says floor here. I guess it should say table in both cases. Two forces act on the ball. The weight force and the contact or normal force is acting on the ball while it's in contact with the table or floor. Which force imparts a greater magnitude impulse to the ball during that brief time of contact? The weight force, the contact force, both are equal or not enough info is given. The answer is the contact force does, and in this case, probably the most straightforward way to see it is that the ball was going down and it ends up going up, so it had a large acceleration in the upward direction. And what that means, if it has an acceleration during contact in the upward direction, the upward force, which is the contact force, must have been a lot bigger than the downward force, the weight force, to give it a net acceleration or acceleration in the upward direction. So the contact force has to be a lot bigger than the weight force because there was a huge acceleration, a big change in velocity over a very small change in time. What that means is that compared to the contact force, the weight force, at least if we're just considering the small amount of time in which the ball is in contact with the table, the weight force, we can kind of ignore it in terms of the impulse it delivers to the ball. The contact force is the only important player here. And that has to do with something called the impulse approximation that hopefully you read about in the reading. If we have a quick collision, two things smacking right against each other, there might be many forces acting on each of the colliding objects. For example, the two objects are colliding with each other, so there's some contact force between the two surfaces of the object. Gravity might be acting on them. Maybe they're colliding vertically as one's moving down and one's moving up near the surface of the Earth. There could be kinetic friction or air drag. Kinetic friction if they're sliding pucks traveling toward each other, air drag if they're moving through the air. Lots of different forces that are acting. in the very, very short time of the collision, from just before they contact until just after they separate, all of the non-contact forces, the friction forces, drag forces, gravity forces, any other forces that aren't the collision contact forces, are so small during that time compared to the collision contact force that we can ignore the impulse that they give to each of the two colliding objects. So in applying the impulse momentum theorem, or we'll find out later on in the general statement of the conservation of momentum, if we're considering a quick collision, so we take initial to be just before they contact, final to be just after contact, that delta t is very small over which we're calculating impulses. And those other forces, air drag or friction or weight forces, just don't have enough time to impart a significant impulse to the objects. So we can totally ignore them compared to the impulse that one object exerts on the other through the contact force. That approximation of ignoring all the non-contact forces in a very quick collision is called the impulse approximation, and it simplifies our life a lot of the time. The upshot is the other smaller forces just don't have enough time to deliver a substantial impulse. The weight force can deliver a substantial impulse to an object that's falling a long distance from the top of a building, but in a very quick collision, there's just not enough time for the weight force to have a big enough delta t being multiplied by it to give a substantial impulse compared to the impulse being delivered by the contact forces. So we're going to use that in a couple of problems now. I want you to go to the next worksheet problem. It concerns a 3 kilogram ball bouncing on a hard horizontal floor. We'll take plus y to be up. Just before one of the bounces, at the point where it just begins contacting the ground, it's moving down at 2 meters per second. It's in contact with the floor for 1/100th of a second, and it leaves the floor moving at 1.8 meters per second. So this is not a perfect super ball. It loses a little bit of speed from going down to going back up during the bounce. And there are some questions that you're supposed to answer here, and I think we're supposed to do all parts of problem 2. But the first one is what net y impulse component is given to the ball during the bounce. Do that and we'll be back with the solutions.